In this tutorial, we will be working through the solutions to the short answer section of the 2020 QCE Specialist Mathematics Tech-Active exam. If you are looking for solutions to the multiple choice questions, check out the link in the description below. We will also find links to the official QCE exam papers. The technology being used in this tutorial is the TI-84PlusCE graphing calculator. So let's get started. Question 11. This question relates to dominance matrices. We are given information about the results of 5 teams playing one another in a competition. Part A asks us to populate the dominance matrix based on the information provided, where 1 represents a win and 0 represents a loss or no result. The rows reference the winning team and columns the losing team. The first piece of information tells us that A defeated D. So we put a 1 in row A under column D. As this is the only win for team A, the remainder of this row is filled with zeros. The next piece of information tells us that B defeated A, C and E. So in row B we put 1s corresponding to columns A, C and E, and populate the rest of the row with zeros. Row C has a 1 for columns A and E. Row D has 1s for column B, C and E. And finally, row E has a 1 for just column A. We don't need to create the matrix on the calculator to answer part A. However, it will certainly save us time for part B. Part B requires us to rank the teams based on the model n plus n squared. I can do this on the calculator. To establish the ranking, I need to add up the values in each row. You could do this manually or simply multiply by a column vector. This result tells me that D is the highest ranked team, followed by B, and A and C are equally ranked, and then finally E is last. Part C. This asks us to comment on the ranking model, specifically identifying the limitations. Our attention is immediately drawn to the tie between A and C. If you look back at the original results, Team A won just 1 game, whereas Team C won 2. So the limitation of the model is it's not able to distinguish between the ranking of A and C. Before we move on, and to help us answer part D, let's pause for a moment to understand what n squared actually tells us. N squared calculates second order dominance. So let's suppose you're a player on Team A, and this week's match is against Team D, which you happen to know have already defeated Teams B, C and E. So you would assume this is going to be a tough match. If your team goes on to beat Team D, then you might make some assumptions about your team's ability over B, C and E. This is called second order dominance. We can see second order dominance in a network map. We are told that A beat D, but D beat B, C and E. This dominance is represented in the second order dominance matrix. In a nutshell, the second order dominance assigns a level of kudos, if you like, for beating a team that has displayed some dominance over other teams. This leads us to part D. The ranking model provided by the organisation places equal weighting on beating a team directly as it does defeating a team that has already beaten other teams. Assigning coefficients, on the other hand, can reassign this weighting. For example, a 70% weighting for directly defeating a team and 30% weighting for defeating a team that has defeated other teams. So, using this weighting via some coefficients, we get a new order of D, B, C, A, and E. So we can see that the preference is given to Team C over A, acknowledging that whilst A defeated the rather dominant D, Team C actually won more games. Question 12 is about differential equations. We are provided with an equation that describes the rate of change of yeast cells over time. Part A instructs us to show that. Show that questions are often used where subsequent questions rely on the answer, so even if you can't do Part A, you're not excluded from Parts B, C or D. The differential equation we're provided with is given as a rate dn on dt, but the equation is given in terms of n, so we need to flip the equation. The question also provides us with some scaffolding in the form of given 1000 over n times 1000 minus n, we can use this information to separate the fraction and therefore use two separate integrals. The two integrals give us some logarithms, and these can be combined using our log laws. Move the constant across, and we have the final equation as required. Part B provides information so that we can find a specific solution to the differential equation. We could use the calculator's solve command here, but again the question says show that, so we need to show the working. We also need to be careful because the question also says a scientist commenced the experiment. And finally, look at the way the answer has been expressed. N equals. So, the relationship we have is t in terms of n rather than n in terms of t. So, the first step, rearrange the equation to express n in terms of t. Transposing, we rewrite the equation with exponentials rather than logarithms. We have two occurrences of n, so flipping both sides will allow us to cancel down the n's. Add 1 to both sides, flip to get n back in the numerator, and multiply both sides by 1000. Now we can substitute the initial conditions back into the equation. As the denominator needs to equal 10, we can see e to the power of negative c must equal 9. The equation is now equal to the one provided in the question. Part C. Determine the time of day when 900 yeast cells are present. In other words, find t when n equals 900. We could use the relationship provided in Part A, where t was expressed in terms of n, but that would rely upon knowing the value for c. By using the equation in Part B, we're not relying on any of those sorts of calculations. So I'm going to use the solve command and determine the value of t. We can see that t is approximately 4.394. But this question is worth 2 marks. we should suspect that more calculations might be involved. So let's go back and reread the question. We're asked to find the time and recall that the experiment commenced at 9 AM. So we need to add the 4.3 hours to 9 AM. Part D. Scientists predicted that the number of yeast cells would eventually exceed 1200. Eventually, in the context of time, means consider what happens to the function as t gets larger, or tends to infinity. Let's return to the equation given in Part B. What happens to e to the power of negative t as t gets bigger? So this part of the expression tends to 0. 9 times 0 is 0, so we're left with 1000 divided by 1. So as time goes on, the number of yeast cells approaches 1000. To exceed 1000, we'd need the denominator to be less than 1, which is not possible. So we conclude that the scientist's prediction is not reasonable. But as the question is worth 2 marks, we need to provide the evidence in our conclusion. Question 13. This is a probability question. We are told that the speeds of the cars on a particular highway are normally distributed, with a mean of 98.7 and a standard deviation of 4.1 km per hour. A police officer records the speeds for 20 randomly selected cars. We are asked to find the expected number of cars in the sample that will be travelling within 1 km an hour of the average speed. So, we'll start by calculating the probability of a single car travelling within 1 km an hour of the mean speed. For convenience, I'll store the mean in U. So, we see the probability of a single vehicle travelling within 1 km an hour of the mean speed is 0.193. Therefore, in our sample of 20 cars, we would expect to see approximately 4 cars. Part B wants to know the probability that the mean speed of this sample will exceed the speed limit. This section refers to the sample mean, not the likelihood of an individual vehicle, but the likelihood of the sample mean. The sample means will be normally distributed with the same mean as the population mean, but the standard deviation is equal to 4.1 divided by the square root of 20. Now we can work out the likelihood of finding a sample mean that exceeds the speed limit. And so we get a probability of 0.078. Part C. This question is asking us to imagine that we have a sample with an average speed that is higher than some value k, and that there is only a 5% chance of finding a sample just like this one. So what is this value of k? Well, we have been given the likelihood of our sample, so we are using the inverse normal. The area we are using is 0.05. We are still talking about a sampling distribution, so we use the population mean and the standard deviation of 4.1 divided by the square root of 20. And we want to work out the region to the right, as the question refers to exceeding this value. This gives us a score of 100.2 kilometers per hour. Question 14. This question is about a probability density function in the form of an exponential function where t, measured in months, is greater than 0. Part A asks us to show that this is a probability density function. Show that means we need to perform some calculations and include the corresponding working. We know that the sum of all the probabilities must be equal to 1, and since f of t is greater than 0, then we need to show that the integral from 0 to infinity is equal to 1. The integral of 0.16e to the power of negative 0.16t is equal to negative e to the power of negative 0.16t. Now we can substitute the terminals. Negative e to the power of 0 is negative 1, and so we get an answer of 1. Part B asks us to find the probability of cracking the phone screen in the first year. Time in the question is measured in months, so the first year means the integral is from 0 to 12. The definite integral of our probability density function from 0 to 12 is equal to 0.8534. Notice here that I left the problem as an integral that the calculator can do. This avoids any unnecessary by-hand errors that may have occurred if I substituted values into the expression we obtained in Part A. Of course, you can also use that as a way to check your by-hand integral in Part A. Part C. In this question, we are given the probability as 0.75. We are trying to find the value of m such that there is a probability of 75% that the screen gets cracked between 1 and m months. Once again, I could use the expression obtained in Part A, or I could just use the numerical solve option and a definite integral. I know the value of m will be greater than 1, and based on our previous calculations, probably somewhere around about 12. Solving for m gives us a result of 14¼ months. Question 15. This question provides us with two position vectors, OP and OQ. The TI-84 Plus does not have any inbuilt vector functionality, so by hand calculations are probably the most expedient method to solve this problem. However, just for fun, I'll demonstrate how these calculations could be done. OP and OQ can be written as matrices or lists. For this example, I will use the lists. To determine the angle, POQ, we need to calculate the dot product of OP and OQ and their respective magnitudes. For the dot product, simply multiply list 1 by list 2. We see that each element in each list is multiplied, the same as multiplying the I components, the J components and the K components in any by hand calculation. Now, sum the results, and we get -6 for the dot product. Next, we need to calculate the magnitude of each vector. To do this, we square each component, sum them, and then take the square root. I can do this using the lists also. Now we have all the components we need to calculate the angle. So the angle between the two vectors is 109.1 degrees. Make sure you know whether your calculator is in degrees or radians. The question doesn't specify the angle format, so make sure you include either the degree or radian symbol in your answer. Part B. This question asks us to find the area of the triangle formed by points O, P and Q. We can use the formula a half AB sine C, since we already have the magnitudes of the two sides and the included angle. And so we get an area of 8.66, which looks remarkably like 5√3. Another way to work out the area of the triangle would be to use Heron's formula. For this we would need the third side, PQ, which of course is equal to OQ minus OP, or in other words, list 2 minus list 1. I'll store this in list 3. Now I can store all the magnitudes of these vectors, or their lengths, in A, B, and C, and the semi-perimeter in S. Now, using Heron's formula, we get the same result as before. Using Heron's formula to calculate the result took an extra minute or so. We got the same answer as we did before, so now we're confident that not only was this answer correct, but also the previous one as well. Question 16. This question prompts us to use de Moivre's theorem to prove the identity shown. The theorem states that z to the power of n is equal to r to the power of n cis n theta. In this case, we'd say that r equals 1 and n equals 4. The identity provided in the question does not have any imaginary components, so we can focus on equating just the real components. As we expand the right-hand side of the equation, we can remove all the odd powers of sine theta. That leaves us with the expression shown on the screen. Now it's time to look back at the format of the identity given in the question. We need to replace components that are not in the form of cos to the power of 4 or sine squared. The identity that we will make use of here are the various forms of sine squared plus cos squared equals 1. Let's replace the sine squared component in our expression . That fixes one part, as it gives us another cos to the power of 4, but leaves us with a cos squared component. But we can fix that by swapping out the cos squared with 1 minus sine squared. Now we've finished the middle section. It's time to work on the last part, the sine to the power of 4. We can consider this as sine squared times 1 minus cos squared. Again, that fixes another part of the problem, but creates another. Now we have a cos squared sine squared component. Again, focusing back to where we're targeting, we can swap out the sine squared for 1 minus cos squared. Now we're left with one final section, a cos squared, which we can easily replace with 1 minus sine squared. So finally, we have our equation in the form required. That gives us a equals 8, b equals 8, and c equals -7. Now, we couldn't use a calculator so far for this question. However, we can use it to check the answer, which is definitely worthwhile since a question is worth 5 marks. This simple check works to confirm our answers for A, B and C, most likely validating all of our calculations. Part B. There are several ways our results could be checked. Graphically, using a calculator, as just demonstrated, or you could do a number of substitutions, which is kind of an abbreviated version of what we just did. Question 17. In this question, we are provided with a differential equation and asked to determine the velocity of the object when it strikes the ground. V represents the velocity and x represents the displacement in meters above the ground. In other words, we need to determine a relationship between x and v. We can start by dividing both sides of the equation by v. Then invert both sides, integrate, and recognise that the integral on the right-hand side is of the form where the derivative is in the numerator and the original function in the denominator. So, our integral is simply the natural log of the denominator. We are provided with some initial conditions, that is, the object was 100 meters above the ground when it was released, but we need to be careful here. The original problem states that v is greater than 0, or equal to 0, which means downwards is the positive direction. So, with the ground being 0, that would mean our initial conditions are x equals -100 when v equals 0. Substituting these values in gives us a value for c. Now, we need to find the velocity when x equals 0. That was our original question. But we don't necessarily need to transpose our equation here. The question didn't ask us to do that. So we can simply use the numerical solver. And we get an answer of 36.73 meters per second. Question 18. There is a lot of information here. The first thing we notice is that we are not given information about mu or sigma, yet the question appears to be about probability, sampling distributions, and confidence intervals. So let's focus on the first bit of information. We are told that the probability of a randomly selected kangaroo having a mass greater than 83.2 is equal to 0.145. I can use the inverse normal distribution to determine the corresponding z-score. Now I can write the equation 83.2 minus mu over sigma is equal to 1.0581. Now I'm looking for another equation involving mu and sigma. The second piece of information relates to a sample of kangaroos. Here I'm told that the probability of the average mass of 12 kangaroos being less than 74.1 is 0.079. Using the same approach as before, the z value is -1.4118. Now I can write the second equation. 74.1 minus mu divided by sigma over root 12 equals negative 1.4118. I need to solve these equations simultaneously. Whilst there are several ways I could do this on the calculator, it's quicker in this case to just transpose at least part of the equation to make sigma the subject for each. I can still use solver. Now my value for mu is 76.6304 and it's automatically stored in U. Substituting that back into one of my previous equations, I get sigma equal to 6.2087, which I'll store in S. Now let's have a look at the next part of the question. We're told that a 90% confidence interval for mu has been calculated using a sample of n kangaroos. The sample has a mean mass of 79.1 and a standard deviation the same as our population standard deviation. We are also told that the confidence interval does not contain the population mean. Let's take a look at this for a moment to see what's going on. The red graph is for our kangaroo population. The blue graph is for a sample of size n with a mean of 79.1. And the shaded region and corresponding vertical lines represents our 90% confidence interval. As I change the size of my sample, the shape of the distribution changes because it's causing the standard error to change. The larger sample produces less variation about the mean. So, for a certain value of n, we see that our sample will no longer contain the population mean. So, we can use the inverse normal distribution to see that a 90% confidence interval is the region corresponding to plus or minus 1.64485 standard deviations from the mean. The mean for our sampling distribution was 79.1. It must be 1.64485 standard errors from the population mean of 76.6. As we are told that sigma is the same as before, 6.2, so we get the equation 79.1 minus 1.64 by 6.2 over root n is equal to 76.6. Solving this for n gives us 17.1. Based on our diagram, selecting a sample of 17 kangaroos would allow our confidence interval to spread out just enough to include the population mean. So, we need to choose at least 18 kangaroos for our sample. Remembering, we're not supposed to include the population mean in our 90% confidence interval. There is another way we can check our answer. We can use the Z interval on the calculator. We know the statistics, and sigma equals 6.2, and the sample mean is 79.1, so let's try a sample size of 17 and a confidence interval of 90%. The interval it returns just includes the population mean of 76.63, as we expected. If we repeat this process with n equals 18, we see that the 90% confidence interval no longer includes the population mean. So our answer is n equals 18. Question 19. Just like the previous question, There is a lot of information to take in here. These are the sorts of questions you want to ponder during reading time. Much of the information relates to the diagram. So let's jump straight into what we are trying to find and figure out what we need to do in order to get there. We are asked to find the acceleration of the vehicle. We're told where the vehicle starts and that it accelerates at a constant rate, and that the projectile lands right in the middle of the vehicle. Let's call the position where the projectile lands on the vehicle as point P. If we knew the coordinates of point P, then we could work out when the projectile would be there, or vice versa. Knowing the time would help us work out the where. This combination of information would allow us to determine the acceleration of the vehicle. So our focus shifts to calculating P or T for the projectile, leaving the cart alone for the time being. To calculate P or T for the projectile using vector calculus, as the question instructs, means we must determine the launch velocity. We have information about the launch speed through the circular motion that initiates the projectile launch. For the speed, we know that the projectile is being spun around in a circle of radius 0.5 meters every 0.24 seconds. This means that the projectile covers pi meters every 0.24 seconds, so it has a speed of 13.09 meters per second. I'll store this as v. Now we need to figure out the launch angle. To help us calculate the launch angle, we can use the information or diagram that tells us the object clears the pole. Now we need to set up a frame of reference. I'm going to set the origin as the point of release, which is 0.3 meters above the ground. So therefore, the point the projectile will pass through will have coordinates 14, 1.75. We can now start working with the position vector. With the origin at the launch point, we have the horizontal or I component as Vt cos alpha. And for the vertical component or J component, we get Vt sine alpha minus 4.9 t squared, the 4.9 being half of g. We now know that R of t equals 14i plus 1.75j, its position when it clears the pole. This actually gives us two equations with two unknowns. For the I component, it's relatively easy to transpose to make t the subject. I'm going to store that equation in y1. It makes a handy way to copy and paste. I'll use A to represent alpha. Now, if I go to the numerical solver, I can work with the J component, V times T, which we stored in y1, times by sine alpha minus 4.9, and again recall the equation that I stored for t, squared, and we see that the equation passes through 1.75. So solving for A or alpha, I get 36.92 degrees. Notice my calculator is in degree mode. Now we have the complete vector equation for the projectile because we worked out its initial speed and its launch angle, giving us the velocity. At this point, it's worth checking the equation. I'll use the parametric mode on the calculator, storing the I component in x of t and the j component in y of t. Set the window dimensions and graph. With the initial velocity locked in, we know the projectile will land on the vehicle when it is 0.1 meters above our launch height, our frame of reference. The quadratic expression tells us to expect two answers. From the animation, we can see that it will be 0.1 meters above launch height on the way up, and then again on the way down, which is the one that we want. We can use the numerical solve routine again to get the second time. We make y of t equals 0.1, and solve for t, with t being greater than, say, 0.5 seconds. So we see the projectile will reach this height after 1.592 seconds. Now we know the time. We can substitute to get the horizontal position. We see that the horizontal position of the projectile at this time is approximately 16.66 meters from the starting point. The centre of the trolley starts at 14.3 meters from the launch position. So the centre of the trolley therefore needs to travel 2.36 meters in the 1.592 seconds it took for the projectile to get there. As it is starting from rest, this gives us an acceleration of approximately 1.86 meters per second squared. So it got there. Now that we've finished the question and the exam, let's take a moment to check this question. It involved a lot of calculations, and we can use the calculator to see if our answer is at least approximately correct. The parametric mode is already set up for the projectile, so let's just add in the equation for the vehicle. The vehicle equation is relatively straightforward, pardon the pun. We set the original starting position as 14.3 meters from the origin, and I'll set the calculator to run the equations simultaneously, so we will see the projectile meet the vehicle. Well, that's all for this exam session. Hopefully you're able to follow along, check your answers, and maybe pick up a few calculator tips along the journey. Be sure to subscribe to our channel so you'll be kept up to date as new tutorials are added to this series. Thanks for watching.